Hello, you're welcome back. All right, so we'll continue from where we stopped. So here we're going to be looking at tensile stress and tensile strain, okay, of elasticity. All right, now as we already defined, elasticity is the ability of a material to regain its original shape after being distorted. Okay, so what simply means that if you want to actually measure material strength, because it's really very necessary in engineering, okay, before you can actually use a material for any construction, you need to measure the strength of that material. Now one of the strengths, okay, of a material that is measured is the stress that the material can withstand per unit area of the material, and of course the strength, okay, that material could actually produce. Okay, so let's get to it. What is tensile stress? Okay, now tensile stress is defined as the force per unit area of a material, force exerted per unit area of a material. So, and of course force is measured in newton and area is measured in meter square. Okay, so that means tensile stress is newton per meter square. And of course you know very well that in physics there's another quantity that have the same dimension. Pressure is also measured as force all over area. Okay, so it simply means that stress on an object or a material is the same as the pressure on that particular material. Okay, so now let's look at the strain. Okay, please pardon me, let me get something here. Okay, so let's look at the strain. All right, strength is actually defined as the extension that is produced in the material, the extension that the material can actually produce, okay, per unit length of the material, extension per unit length. Okay, now since extension is measured in meters and length is in meters, that simply means that strength doesn't have any unit, tensile strength. Okay, now the ratio of tensile stress and tensile strength is what is known as the Young modulus. So the Young modulus of a material, Young modulus, is equal to the stress of that material then divided by the strength. Okay, so if you are to evaluate your modulus, you first evaluate stress, evaluate the strength, then you can now get the your modulus. Okay, so I believe that so far so good. I've actually given you the vital formula in this particular topic, so we need to solve questions. So I have to get to a place where we have elasticity question so that we can solve question in elasticity. Okay, all right, think almost there. I'm almost there. Okay, can I just okay, I think I can do justice to this question now. All right, okay, I hope you can see it. I have to expand this so that it can be seen well. You can see it very well. Okay, so here we go. It goes this way. A string of length 4 meters is extended by 0.02 meter when the load of 0.4 kg is suspended at its end. What will be the length of the string when applied force is 15 newton? Okay, so let me clear my screen so that we'll solve that question. So a string of length, so the original length, I have to write my parameters first. The original length of the string is 4 meter, comma, okay, it's extended by 0.02 meters, so the extension is 0.02 meter. All right, when a load of 0.4 kg, so the force, let me call it F1 because I was told that two forces was applied to it. Let me call this one F1. So it's a load of 0.4 kg. So remember, I have to convert the kg to Newton because force is in Newton, right? So what I would do, I multiplied by the 0.4 by 10, and that gives me 4 Newton. Okay, so now what are we looking for? So what will be the length of the string when I apply force is 15 Newton? So we are looking for the length of the string, that is let me call it L2, at the point where F2, okay, is 15 Newton. So of course, if I want to get this F2, okay, remember the formula is still gonna be equal to K. All right, then bracket open the original length. Let me call the original length L1. L1, the original length, please pardon me, according to Hooke's law, is gonna be L2 minus L1. Okay, so it happened that force F2 and no F2. Of course, it also happened that the final length and no final length, but something is missing here. That is the force constant. So how will I get the force constant? That is, I'll get the force constant from the initial extension that was produced previously. Okay, so for me to get that force constant, I'm gonna have F1, okay, being equal to, excuse me, being equal to K times the extension, this extension. So I'm gonna get the K now. K now is gonna be equal to the F1 all over the extension. Okay, so F1 is 4 Newton, the extension is 0.02 Newton. So when you do this, what you have is going to be 200 Newton meter. So the force constant of the string is 200 Newton meter. So having gotten the force constant, I can get this out. Okay, I can apply the formula here so that I can get the final length L2. So F2 is 15 Newton is equal to K, which of course I've already gotten, that gives me 200 Newton. Then I'm looking for L2, then minus L1. What's my L1? Okay, my L1 is the original length of this spring, which of course is 4 meter. All right, that's 4 meter. Okay, so the original length. Okay, so this is gonna be equal to 15, 200 L2. Okay, 200 times minus 4, that gives me minus 800. So rearranging the equation now, I can now have that this minus 800 goes to the other side of the equation. So I'm having 200 L2 to be equal to, okay, plus 800 plus 800, of course, plus the 15. That's 815, right? So my final length now L2 is going to be equal to 815 divided by 200. All right, so let's get a calculator. Okay, so 815 divided by 200, 4.075 meter. So that's going to be 4.075 meter. So that is my answer. Okay, so let's get another question. Okay, so this one goes like this. If the force of 50 Newton stretches a wire from 20 meter to 20.01 meter, what is the amount of force required to stretch the same material from 20 meter to 20.05 meter? So it's the same nature of the question. I'll use the force information given by the question to get the force constant. Then I'll use that force constant to get what I'm looking for when, okay, for the second part of the question. So first of all, the force 50 Newton to stretching this material from original length of 20 to 20.01. Okay, so let's do that again. So let me call that force F1. Okay, stretches 20 That's gonna be equal to F1. Please pardon me. I'm looking for the force constant. So the formula still remains K, the L minus L0. So I need to get this force constant. Okay, so what is this force constant? So the force that was supplied was 50 Newton. I'm looking for this force constant. And it stretches the material to, the final length was 20.01 minus the original length, which of course is 20. Okay, so this is going to be equal to 50 is equal to K times 20.01 times 20. That will give 0.01. So that simply means that my force constant, which is the first thing you need to get. Okay, the first thing you need to get is always your force constant. Force constant is the first thing you need to get before you can get any other thing. So that's going to be 50 divided by 0.01, which is 500 Newton per meter. So I haven't gotten the force constant now. It is this force constant now that will help me now get the force that is required to stretch the same material from 20 meter to 20.05 meter. Okay, so now that's going to be F2 now. F2, okay, what is, the question is, what is the amount of force required? So I'm looking for F2 to stretch from 20 to 20.05. So F2 is still going to be K, okay, minus the change in length also, L minus L0. You can use L1 and L2, but any symbol you want to use, but just this is just the change in length, right? Final length minus original length. You can use L2 minus L1, L minus L0, LO. So anyhow you want to do it, but just know what you're doing, okay? So this simply means that I'm looking for this force. I've already gotten my constant. That's gonna be, that's 500 already. Open bracket. The final length I'm actually looking at. What is that final length? The final length is 20.01. 20.01. The minus 20. Okay. So I got to subtract now. So F2 is going to be equal to 500 times 0.01 F2. Okay, so 0.01, right? That should give me, that's 5 Newton. So that force is a force of 0.05. Please pardon me. The extension is 0.05. This the final length of this second extension was 0.05. That's 20 to 0.05. So please pardon my mistake. So what I'm supposed to have here is 500 times 0.05, which of course, if I should multiply that, that should give me 25 Newton. 25 Newton. So I hope that is well understood. Just very simple. Another question. Let me expand it. Okay. Okay, here we go. Okay, goes slowly. A spring of force constant 500 newtons is compressed such that its length is shortened by 5 cm. So whether it is shortened is still distortion. Okay, shortening, compression, extension is still distortion. So both compression and extension, they are still going to be, they're the same. All right. So the question was the energy stored in the spring. So the force constant of the spring is just 500 Newton per meter. Now we are looking for, this time around, is the energy. I've given you the formula for energy. Okay. So two formula for energy. This time around, I'm going to use the second formula I gave you, which of course is half K E square. Because why am I using half K E square? Because force constant was given. So that's going to be half of the force constant, which is 500, times the extension given. This the extension was 5 cm. I need to convert that 5 cm to meter, okay, by divided by 100. If I divide 5 by 100, I'll have 0.05. So that's going to be 0.05. Okay, don't forget it's squared. 0.05 squared. So this is going to be equal to 500 divided by 2. That gives me 250. Okay, then multiply by 0.05 square will give me 0.00, okay, 0.25 if I'm not mistaken. But let me be sure. 0.05 square. 0.0, just 00, okay? Just 00. Alright. So now my final answer is going to be equal to 0.0025 then times 250. What do we have? So that's going to be 0.625 joule. So the energy is 0.625 joule. Okay, as simple as that. Let's look at another question. Okay, so this one goes this way. If a load of 1 kg stretches a cord by 1.2 cm, what is the force constant? Okay, as simple as, okay, ABC, we just apply the Hooke's law formula, F is equal to KE. So we're looking for the force constant. So the force constant of course, is going to be equal to force all over extension. Okay, so here we go. What's the force? Force is 1 kg. Remember, I have to convert this 1 kg to Newton by multiplying by 10. Okay, so that's going to be 10 Newton, then divided by the extension. What's the extension? Extension is 1.2 cm, and I have to convert this 1.2 cm to meter by dividing by 100. That should give me 0.012 meter. I can do that. 1.2 divided by 100, that should give you this. Okay, so my answer is going to be equal to 10 divided by 0.012. So 833, approximately 833. So that's going to be 833 Newton per meter. That is my force constant, as simple as ABC. Okay, then the next, this one is a form of a graph. Okay, it goes this way. The diagram above represents the graph of force applied in a stretching a spiral spring against corresponding extension X. Okay, the force constant of the spring. All right, so the same force constant is still the same formula, but the other thing here is that I'm calculating the force constant from a graph. Okay, force constant is force all over extension, right? But if it's from a graph, it becomes the slope of the graph. That's going to be the change in force, because we don't just have one force in a graph, we have many force. So the change in force divided by the corresponding change in extension. So from a graph, that's how we evaluate it. So let's look at the change in force. From this graph, force changes from 40 to 120, while extension is changing from 2 to 6. So that's going to be change. The final force 120 minus 40, right? From 40, okay? 120 minus 40. Then of course, extension changes from 2 to 6. That's going to be 6 minus 2. Okay, so let's subtract this. This is 80, okay? And of course, this is 4. So if we do this, that should give 20 Newton per meter. So that is what we have, 20 Newton per meter. Okay, is there any other question? All right. Here, a question on your modulus. This one goes this way. A copper wire was subjected to tensile stress of 7.7 times 10 raised power 7 Newton per meter square. Calculate the tensile strength of the wire, given that your modulus of the wire is 1.1 times 10 raised power 11. Okay, I've already given you that formula. Young modulus is always given as stress. Okay, stress all over strain. Okay, all tensile stress all over tensile strain. So invariably now, if I want to get the strain here, I have to making strain, the tensile strain, the subject of formula. Okay, that's going to be equal to tensile stress, then divided by the Young modulus. Okay, of course you can rearrange this equation. I believe you can do what I just did. Okay, all right, so now let's do this. Let's do this. So that's what's my stress? My stress is 7.7 times 10 raised to the power 7. So I write that 7.7 times 10 raised to the power of 7. Okay, then my Young modulus is 1.1 times 10 raised to the power 11. 1.1 times 10 raised to the power of 11. Okay, if we do the 7.7 divided by 1.1, that will give us 7. And of course, you know how we deal with powers of 10 in indices. Okay, since they are divided, 10 raised to the power 7 divided by 10 raised to the power 11, that's going to be 10 raised to the power 7 minus 11. You simply subtract the powers. So my final answer now is going to be equal to 7 times 10 raised to the power of minus 4. And your modulus is measured in Newton per meter square. Why Newton per meter square? Why? Because strain doesn't have any units, but stress here is measured in Newton per meter square. So that's where your modulus is measured in Newton per meter square. I hope that is well understood. Okay. Another question. If a wire 30 cm long is extended to 30.5 cm by a force of 300 Newton, find the strain on the wire. I don't even need to use this force to get the strain on the wire. Okay, I don't need to use the force. Strain on the wire is simple. Strain, to get strain, we know already. To get strain is all we need is just the extension divided by the original length of the wire. Okay, so from what we have there, the extension is simply 30.5 minus 30, then divided by the original length, which of course is 30. That is my strain. So, and let's do that. 30.5 minus 30, that's 0.5. 0.5 divided by 30. Okay, that's 0.017. 17 approximately. That's it. Okay, so we stop here for now. Then we'll do more later. See you in the next video. Thank you.